the strength aspect is mainly done with pozzolans. And these are mineral admixtures. And they're also called supplementary cementitious materials, and there's a common definition that's thrown about. It's in the quotes, and I'm not going to read it because you can read it instead of me saying it. These are mineral admixtures that are put into the concrete, and they can be used in addition to your cement or as partially as to replace some of your cement to make your concrete better. And I'm going to explain what they are, how they work, and the differences between them. Some of them are natural materials, some of them are manufactured, some of them are processed waste products where they're more controlled, and some are waste products that are used with virtually no processing at all. And the ones I'm going to touch on are metakaolin, silica fume, flash, slag, and vitrified calcium aluminosilicates, or also known as VCAS. And there are similar products like VCAS, but I'm going to focus on VCAS. So this is kind of what they look like. Fly ash tends to be sort of a light grayish brown. I've seen fly ash that's almost pale buff. I've also seen fly ash that's almost black. And the color comes from a lot of the darkness comes from carbon content. Metakaolin is very white. Sometimes it's kind of a creamy pink. After it reacts in the concrete, the color goes away. I've made white concrete with metakaolin that looked kind of pinkish cream, and it looked identical to white cement-based concrete that didn't have any metakaolin in it. So the color of the pozzolan when you're holding it in your hand isn't representative of the color of the pozzolan after it's done reacting. Now, fly ash and silica fume, that dark bluish gray one, those colors are preserved. You still see that. Slag is kind of whitish. VCAS is also whitish. I've seen VCAS be kind of grayish, and there's some other waste recycled glass derived pozzolans that tend to be a little bit of a creamy brown because they have a lot of brown bottles in them. So this is basically how they work. When you have water and you have Portland cement and they react, one of the byproducts I already mentioned, the calcium silica hydrates, that's a gel, that's a desirable stuff we want. Well, there's a byproduct, it's calcium hydroxide. And calcium hydroxide isn't terrible. It's not great. It weakens the concrete a little bit, but you still can make decent concrete without dealing with it. But about 15 to 20% of your Portland cement eventually turns into calcium hydroxide. Depending on the cement formulation, it could be more, it could be less, but it's about, let's say, a fifth of your cement. That's a lot. Calcium hydroxide is what makes the concrete very alkaline. That's what gives you the cement burns if you get fresh concrete on your hands. If you've ever taken a piece of concrete out of the forms when it's brand new and run your hand over it, sometimes the concrete can feel slippery. It feels very slick. Well, concrete's not slick. It's not slippery. What you're feeling is the calcium hydroxide dissolving the proteins in your skin. So you're actually feeling your skin dissolving from the high alkalinity. Just like if you've ever splashed bleach on your fingers get slippery. That's your skin dissolving. Well, that's how powerful calcium hydroxide is. When we add pozzolans to our concrete, the pozzolans react with the calcium hydroxide. It's called activation, and it's called alkali activation because it needs a very strong alkaline solution to do it. And that alkalinity reacts with the chemistry of the pozzolan to form more of the calcium silicate hydrate gel, which is the desirable glue that holds everything together. So we're making more glue from the waste product is what we're trying to do. We treat pozzolans just like cement, pound for pound or kilo for kilo. Often we use them as a cement replacement, and I'll explain that in a little while, why we do one versus the other. One thing to keep in mind is that pozzolans take time to react, and different pozzolans can react much faster than others. Most of them react quite slowly. And the different chemistries and all give you different reactivities, as well as the temperature you're curing it at and whatnot. To give you, I'm going to jump ahead and give you a rough idea. you don't even start to see any strength gain from VCAS. This is based on my tests done on cylinders for at least a week, maybe more. So most of your strength, well, all of your early strength, and by that I mean 3 to 7 days, comes from the cement portion in your concrete, not from the pozzolans. There are a couple exceptions. I'm going to talk about that as I go on. So here's sort of a flow chart that the source I got this from was talking about using specifically silica fume to make more durable roads or exterior concrete that's subjected to freeze and thaw. But if you look at it in a general sense from pozzolan, this still holds true. When we add pozzolans to our concrete, we consume the calcium hydroxide, so there's less of it. That creates more calcium silicate hydrate gel that gives us higher strength, helps plug the pores. There's less open space. Calcium hydroxide is a big crystal that's very soluble in water. So once it dissolves, it leaves a big void behind, and that mineral salt, if you will, leaches to the surface and forms part of what you see as efflorescence. Well, those pores are plugged, so our concrete has less permeability, and there are fewer open pores to hold water, and that open water, there's less of it, so we have better freeze-thaw resistance. So there's less free water in the concrete to freeze. Water can't get in. There's not that many spaces for it to be in, so we have better superior durability concrete. And that's the general sense of this is why in a single slide I always use pozzolans in all of my concrete. Pozzolans also, they're physical particles. They're very, very small, and they help to pack as microfiller in between the cement particles and the aggregate. Some of these react to form the gel, and some don't. And so in essence, they're helping to fill in and bridge some of these gaps. So you get a stronger bond between your aggregates and the cement particles and everything else. These are scanning electron microscope photographs of calcium silicate hydrate crystals, and those are those big sort of really sharp, angular-looking, flat, platey things. If you can see my mouse, that's some right there. And this is the outside of a tiny sand grain. This is a pore, an open bubble in the cement paste, and there's some calcium silicate hydrate crystals that have formed. 100 microns, if you could take a human hair and cut it in half, that's the width of a human hair is right there, 100 microns. And then over here we have the big flat platey crystals forming. And these long, slender things that look like fibers are actually eterngite crystals that are formed in the concrete. But mostly what we're looking at here is the calcium silicate hydrate crystals. And these form, they like to form on the surface of the aggregates. So they kind of act like bond breakers that prevent the cement paste from bonding really well to your aggregate, so you get weaker concrete. Well, what our pozzolans do is they consume it, they make it go away, they create more gel, and now we get a better bond, and that's where this better strength comes from. I'm not going to read this list. These are the reasons why we use pozzolans. They're all very beneficial. Because a lot of them are recycled, we're actually increasing the green content of our concrete, and that's important to some people. And as we step through the different types, and I have a little chart of typical dosage, you kind of get a sense of what's used when and where. Probably the most common pozzolans used in construction world is fly ash, but it's not used in concrete countertops a lot, and I think you'll understand why as we step through these. So I use these as a cement replacement. Basically, it doesn't affect my paste volume. I have a fixed amount of cement paste, and part of that cement paste is Portland cement and part of it is pozzolan, but the total volume of it is still the same. So it doesn't mess with my colors, doesn't affect my water cement ratio, it doesn't affect my mix design. All the calculations are very simple. The downside is, as I replace more and more of the cement with pozzolans, I take away the cement that provides the early strength. So high cement replacements yield low early strengths because there's not a lot of cement to hold everything together. You can also add them. Typically this is done if you have let's say you have a concrete truck and it's delivered and you want to add pozzolans to it. Well, you can't take cement out because it's already mixed in. You're just adding bags of pozzolans to that mix. Here you're boosting your cement paste volume, and because the pozzolans are counted as part of the cement in the calculations, your water cement's affected. And of course all your admixtures or doses change and all that. So it's not done as an addition because it kind of messes with all the proportions of everything, but it's certainly not a horrible thing to do. It's just a lot harder to deal with on a mathematical basis. And if you add, since you're not changing your cement content, your early strength doesn't change relative to not using pozzolans at all. But if you add too much pozzolan, the unreacted pozzolans, they don't do anything. Pozzolans on their own don't have any strength. They just act like microfine sand, which may or may not be a good thing. It's never bad to have some microfines, but it's sometimes what can happen. Here's the scenario: is you add too much pozzolan because you're boosting your cement paste and not changing your water cement ratio. All of a sudden, the concrete gets stiff, and the common reaction is to add more water to the mix to boost the paste, get it more workable, and now your strength goes down because you've had to add more water. The proper thing to do would be add more superplasticizer to the mix, but that can be problematic too, just by trying to dose it by eye, as I had mentioned before, with segregation and all that. So in concrete countertops, the two most common pozzolans are VCAS and metakaolin, and VCAS being the vitrified calcium aluminosilicate, and I'll step through what that is. But the reason why these are used is because they're white. There are lots of different pozzolans. Some I'm not mentioning. Rice hull ash, for one. There are a bunch of other ones. They all have different chemistries. And so this little ternary diagram that shows the various major chemical components of the different things. The blue dot is Portland cement. So where the different pozzolans fall on this triangular shaped chart kind of illustrates the components of what the chemical makeup of these. Silica fume, which is a dark gray dot, is almost pure silica. It doesn't have any calcium in it, doesn't have any aluminum in it. Metakaolin doesn't have any calcium in it, but it has roughly equal parts silicon and aluminum in it. And blast furnace slag, the yellow dot, is closest to cement. It almost has no aluminum in it, but it's almost equal parts calcium and silicon. So that's how you read this diagram. I just showed it just for illustration purposes. You don't have to care about any of that stuff. And the PFA means pulverized fly ash. So it's fly ash. Different pozzolans do different things at different rates. That's what all this slide says. So you can't just substitute one for another and get exactly the same results. So let's talk about the individual ones as we go. And this is the most popular one. This is the one that I use a lot. VCAS. It's made. It's a single manufacturer made in Georgia. And what it is it's post-industrial fiberglass waste. It's very finely powdered fiberglass waste. Because they can control the waste stream that they choose, the end product is nearly white. When it's added to concrete, it tends to increase the workability. Therefore, I hate to say that reduces the water demand, because that assumes that you're using water to change your workability, but it's a common way of describing things. In other words, if you use VCAS in your mix, you don't need to use as much superplasticizer to get the kind of workability you want. That would be the better way of describing it. The average particle size is 3 to 8 microns, although just like sand, there's all different size ranges. Typically about as fine or finer than cement. It has good reactivity, which is why it's used. So the reason why it's used is it gives you great workability. It's white, so it doesn't affect your colors. You can make pure white concrete with it. It's a green product. good reactivity, so we have decent early strength. It tends to be used in a slightly higher dose. I'll talk about the doses in a little bit. Before VCAS came on the market, the pozzolan of choice was metakaolin, and it's still a very, very good pozzolan. It's an engineered pozzolan. They take raw kaolin clay. Most of it's mined also in Georgia, ironically, right next to where VCAS is made. And it's calcined, which means it is heated at a very controlled temperature for a very controlled amount of time, and it chemically changes it. So metakaolin meta is Greek for change, and kaolin is a type of clay. So they changed the clay from, you'd never ever ever put kaolin clay in concrete. It would weaken your concrete. But when you use calcined clay, it's chemically changed, it's now chemically reactive. It gives you a very highly reactive, very small particle pozzolan that can actually give you higher early strengths. You can get higher 3-day strengths using metakaolin than you would if you didn't use pozzolans at all. So this is one of the few pozzolans that actually boosts your early strength. Probably the one reason why it fell out of favor is because it's engineered from raw materials. It's technically not green. Or as green, let's say, although it's a very fuzzy topic that I'm not going to jump into. And it tends to make the concrete sticky and reduce your workability, which is actually useful for some things because it kind of can act like a viscosity modifier in your mix. Prior to metakaolin coming on the market, the only really high-performance pozzolan that was available, and not very readily available, was silica fume. Historically, the only silica fume that was available was the normal stuff that's sort of a dark bluish gray. There's a photo up top of there's a white silica fume and a gray silica fume. And the white silica fume is much more expensive, but equally as effective. Silica fume has been historically used to make ultra-high performance concrete where you're pushing 10, 15, 20,000 psi concrete. Very, very high. It's used in oil rigs and nuclear reactors and stuff like that where you need very, very dense, very strong concrete. Average particle sizes are smoke size, 1/10 of a micron. Very, very small. Fraction of a human hair. You get very high reactivity. But the trade-off is it can make your concrete very sticky if you use it in high quantities. So it's described as having a very high water demand. Again, that very bad habit of using water to change your workability. I've used silica fume in the past. I've blended it. You can blend. The great thing about pozzolans is you can blend them. Now, getting into blending means you're starting to delve into a world of, are you changing things and is it getting any better? One pozzolan is perfectly good. 3 just makes it more complicated. It's not necessarily going to make it better for your customers. There is a brand of pozzolan sold on the market called Altopoz that's a blend of VCAS and metakaolin. Don't know what the proportions are, but that's what it is. You can make your own because that's what the ingredients are. There are blends of silica fume and fly ash and slag and silica fume and fly ash and whatnot. You can go on and drive yourself crazy sourcing and blending all these things till the sun comes down. In the end, what we want is good, strong concrete that we can get out the door quickly. And adding an extra pozzolan doesn't necessarily mean we're going to make extra better concrete. It just means we make more complicated concrete. So I'm going to get off that soapbox and talk about fly ash. It's, again, the most popular and most commonly used pozzolan in the construction world. And that's because fly ash, there's a lot of it, comes from burning coal. And coal is burned for power in a lot of places in the world. And there's a lot of fly ash generated. And unfortunately, most of the fly ash that's generated is still landfilled. the flash industry is trying to get, use as much of it as possible in concrete, and it's a very economical way of making your concrete less expensive. So instead of, let's hypothetically say, I want to make a 4,000 psi mix or 4,500 psi mix, which would be 30 MPa in round numbers, and that's all I need. Okay, so that might be a driveway, that might be a house foundation or something like that. You can order concrete made with 100% Portland cement that does that, and it's going to cost a certain amount. But if you ordered it with flash as a substitute for some of your Portland cement, the per volume cost of that concrete is going to be lower. Now the end result, the 28-day strength of that concrete might be the same, but the early strength is going to suffer. Flash has a slow reactivity, so you're going to lose early strength. It tend to be used in high substitutions. One of the benefits of using flash is because these are small glassy beads, they look like tiny ball bearings. It adds a lot of workability to the concrete. You can make very flowable concrete. The reason why it's not used in concrete countertops is because it's a completely non-refined product. One source might be the color you see in the picture, another source might be black. Next year when you get it, might be a different color. So you have no control over your colors or the shade of your colors, and you lose a lot of early strength. The reactivity is very slow. So, you might not even start to see a recovered strength for a month or so. Well, that's too long. It's fine for the construction world, but not fine for us. And then another pozzolan that's a pure waste product is called slag. It's technically called ground granulated blast furnace slag, or GGBFS, and it comes from the refining of steel and iron. So when they're melting steel, or they're taking raw iron, they're turning it into steel, they have to control the oxidation of it, and so they melt. They put in limestone and they put in some other kinds of minerals that act as a flux. So this rock melts on top of the big kettle of molten steel, and not only does it block the oxygen from getting to the steel and causing it to oxidize, but it also acts as a sponge to help suck impurities out of the steel. Well, once they're done cooking the steel and doing whatever they do to the steel to get it the way they want it, changing the chemistry of it, they've got basically man-made lava. It's liquid rock. They have to do something with it. Well, if they just pour it into a big slag heap, it basically forms man-made lava. Well, to get rid of it, since there's a lot of it made, they can spray water through it and turns it into granules. And that chills it really fast, so as the rock cools, or the liquid rock blend that has all the stuff in it, as it cools, it basically changes its chemistry, so it becomes reactive. And it becomes reactive when it's ground up into a fine powder, and it's ground different degrees of fineness, and that's why there's different grades of it. The finer you grind it, the more reactive it is. The chemistry of slag is such that it has a little bit of calcium oxide in it, so it is self-cementing to some degree, and it tends to be used in high replacement doses. It adds workability, which is why it's used. It can improve a lot of properties of concrete, but it's not very reactive as compared to Medikill and silica fume. So you have slower set time, slower strength gains up front. Again, in the construction world, it doesn't matter, but for us it does matter. Perhaps one of the biggest reasons why I'm not a big fan of it is there's a definite greening effect. Slag tends to have a lot of iron and manganese sulfides in it, and how much depends on the kind of steel and what they're making. Again, because it's just a sponge to suck all the impurities out of the steel. Well, we're using that sponge that has all those impurities in it as our pozzolan. Who knows what it is, and who knows what the steel was when we get it. So its composition can change from source to source and from time to time. And these sulfides, when they react with water and the alkalinity of the concrete, they can turn green. And I've seen slag cement look, like seaweed green. It can look kind of nasty, and it takes time and air and oxidation for that greening to go away. Sometimes it looks bluish. That might take a few days. I've seen concrete where it doesn't go away. Some concrete, countertop concrete made with it, I've seen it go away too. But it's a possibility. It's a real possibility. And there's actually an association, the Slag Cement Association, that talks about the greening effect and how over time it will disappear. But when you strip the forms, you're going to see this green blotchiness. Something to keep in mind. So when you're adding these pozzolans to your mix, when you blend them into your mix and formulate your mix, they're going to have different effects. And so this is from the Portland Cement Association. It certainly doesn't cover all the pozzolans I use, but it's not, VCAS is not on here, but you get a general sense of what's going on. So the water requirements for flash and slag are lower, silica fumes much higher. I would say that if you add VCAS, your workability is going to increase just like slag and flash. Plastic shrinkage, cracking, all these things, set time and all that are affected differently. Again, the way pozzolans work is they need calcium hydroxide to be activated. They don't do anything on their own. Calcium hydroxide is generated as the cement hydrates. That takes time. So nothing happens instantly. And the more pozzolan that replaces cement, the less cement there is to generate calcium hydroxide. And it takes a certain concentration of calcium hydroxide to kickstart that pozzolan to turn into the calcium silicate hydrate gel. So if you have a very slow reacting pozzolan that you use a lot of as a replacement, you only have a little bit of cement, so your early strength is going to be lower because you only have a little bit of cement to provide that strength. And then it takes a long time for that strength to build up to where it exceeds the strength of the concrete that it would have had if it was only made with cement. So that's why I don't like to use slow reacting pozzolans, because they have a big negative effect on your early strength, and that's what's everything, to me at least. And here's some typical doses. Now, different people use different doses, and you could do whatever you want, but these are the typical ranges. For VCAS, in my precast mix, I use 15%. I've gone down to 10%. I don't like to go up above 15% because I'm starting to lose early strength. In GFRC, I use 20% replacement because I have all those fibers to help boost my green strength of the concrete. I don't have that in the precast. Metakiln, because it's much more reactive, 10 to 15%. Typically, I've done 10%. Silica fume, 5 to 10%. 10% is a lot. 10% is a lot. Typically, it's 5 to maybe 7%. And then I don't have that much experience with slag, but some folks have gone less, some folks have gone more, but 30 to 45% is roughly what the construction industry uses as a replacement. I've seen mix designs that use 100% slag. I've seen mix designs that use, say, 75 to 80% slag. But that's the kind of concrete that you would never want to make concrete countertops out of. It has a different purpose. It runs on a different time scale. So that's another thing to keep in mind is we work on a different time scale. Our needs are different from the construction industry, so we just can't simply pick and choose arbitrarily. And of course, all these, again, are as a cement replacement, not as an addition.